All right. All right. Welcome, guys, to STEM Friday. Some of you, I know it's not your first rodeo here with us in this setting. So welcome back, the new people. Thanks for joining us, and we hope to see you at the others that we have all the way up into May. So we have plenty more for you to see, but Gabriele is a treat. He's here from the LIGO laboratory in Pasadena. Um, we're going to talk about gravitational wave astronomy today. Um, the chat is disabled for now because some people in the past, you guys know. And so if you need, I'm going to leave the unmute on your own. I'll keep it on. I'll keep it enabled, but if somebody interrupts him, of course, I'll disable it. So be nice and welcome our guest, Gabriele Vajente. How is it, Vajente? I
Vajente.
Vajente. I mess this up every time, and I apologize, but I had it one time, I think. But we call him Gabe for short, but he's Gabriele. So that being said, welcome our guest, Gabriele.
Thank you, Adrienne. Thank you very much. Thank you, everyone, for deciding to spend some time with us. It's going to be interesting, I hope, and I'll do my best. So today, I want to spend some time with you and explaining to you what gravitational waves are and why I think this is an exciting topic and what we're doing to understand more about our universe using gravitational waves. But first of all, let's go and look back in history, right? So humans have always been excited to understand more about our universe. If you live a little bit outside of town and you can look up at the night sky, you see a lot of stars. And so it's natural to ask yourself, what is out there? What can we learn about the universe? How does all of that work, right? And as soon as humans were able to do that, they started studying the universe. And it's natural for us to do that using light. So we use different kind of light, first with our own eyes, so the visible light. But then with the years and the decades and the centuries, we learn to build instruments and we discover that there are more colors to the light. There are more components to the what we call the electromagnetic spectrum, so different kind of lights. So we learn that we can look at the universe beyond what is visible with our own eyes and see a lot more. And you see those different pictures, every one of those pictures is a representation of all our night sky if you were able to see it in the visible light, in the infrared, in gamma rays, in microwave, and so on and so on. So you can see that every time we manage to open a little bit a new window into different parts of the electromagnetic spectrum, different kind of lights, we were learning so much more about our universe. Well, today, I don't want to tell you anything more about light or electromagnetic spectrum because we are going to try and see what we can learn about our universe in gravitational waves. There are still waves, but they're about gravity. So, of course, the picture you see here is just some imaginative representation by Van Gogh, which has nothing to do with gravitational waves, but just like the mystery that you see in the swirl in the sky. So I guess what are gravitational waves? Well, you can look at the term and say, okay, we have gravity and we have waves. So let's start with waves, which is kind of simpler. So we all know what waves are, some sort of periodic oscillation that can travel through matter or through space or a lot of other media. So for example, sound is a wave, a pressure wave in air. And now I am here in my office, I produce sound, these pressure waves in the air, then those got converted into electric waves by my computer and sent with radio waves all the way to your computer so that you can listen to me. Ocean waves, earthquakes, they're all different kind of waves. But again, light and radio waves, different kind of electromagnetic waves. An important thing to know here is that waves can interfere. So if you have two waves that are traveling together, like in the animation down here, it can happen that the two waves, they go up and down at the same time. And so they reinforce each other. When they sum together, they make a bigger wave. Or it can happen that when one wave goes up, the other goes down. And then if you sum up, they're always canceled out and you got nothing there. This is what we call destructive interference, because they interfere with each other and they cancel out. So that's something important to remember later. But waves, we know that. We're used to waves. We see a lot of them. Gravity, maybe you think you know very well what gravity is, and a lot of people in our past thought that they knew exactly how gravity was working. Aristotle, the Galileo Galilei, then Isaac Newton. Well, we have to get to Albert Einstein, and I'm sure you heard his name a couple of times in your life, that more than 100 years ago gave us what is still, as of today, the best explanation of how gravity works. So Einstein understood that gravity is not quite a force that pulls things together, that keep you from flying away into space, but Einstein understood that large masses, like Earth in this case, in this animation, deform space and time. So imagine if our universe was like a big rubber sheet, right? And you put a big ball in the center, this will bend the otherwise straight rubber. And then if you have a little marble and you throw it on this plane, it won't go in a straight line because the rubber itself is curved. And so this little marble will go in circles because even though the marble wants to go straight, the space itself is curved. Same things happens in the universe. Earth and the sun and every big mass bend the universe, the real fabric of space and time. And then objects like the moon or Earth, they think they're traveling straight, but actually they're going in orbit because space is curved. So every heavy object, like stars, big objects, curve the universe, curve space and time. So now you can imagine if there are two stars, like in this animation here, that are orbiting one around each other, each one will create their own deformation of space and time. But since they're moving one around each other, they create ripples in space and time that then travel away at the speed of light. This is what we call gravitational waves. So here's the idea. Every time you have two big objects, like two stars, moving one around each other, those create gravitational waves, ripples in space and time that travel away at the speed of light. So those are gravitational waves. So here comes the first story I want to tell you. So this is a story about the very first time we ever saw the effect of those ripples, those gravitational waves here on Earth. And this is a story that starts a long, long time ago when there were two black holes, so two big objects that were orbiting one around each other. Black holes are much bigger than stars. As they orbit around each other, and you see an animation here, this is not a real image, it's just a representation, right? The two black holes, they're orbiting one around each other, and then they form space and time. As they do that, they create gravitational waves. And as the more and more gravitational waves they meet, the closer they get until they merge and they create one big gigantic black holes. So this is the origin of the very first gravitational wave signal we ever saw. So you might ask yourself, what is a black hole? Well, to cover that, let's give you a very brief lecture on the life of stars. So stars are formed from a cloud of gas that then contracts, collapse due to gravity, and you can create either a small star or a fairly large star. So the sun, for example, is a fairly small star. Then the star is kept together by the pressure of the nuclear radiation, the nuclear explosion in the core, that balance out gravity. Gravity would like to compress everything down, pulls everything together, but the nuclear reaction push back, and this is a balance. When the fuel in the center of the star finish, then there are no more any nuclear reactions, and so gravity wins, and it makes the star collapse. So at some point, this will explode, eject some of the external part of the star, and then if the star is like the sun, it will create just a white dwarf. So a cold ball of matter that slowly will, become a gray dwarf and then a dark dwarf and will just disappear and just be there in the universe doing nothing. But if the star is bigger, then you will have a supernova explosion, much bigger explosion. And then what remains of the star after this explosion will be pulled together and made collapse by gravity. But at that point, gravity is so strong that nothing can stop it until really the electrons in the atoms fall inside the nuclei of the atom and they create a big ball of neutrons. Even that cannot be stopped if the star is really big, and even the neutrons will be squashed together, and at the end of the day, everything is collapsed into a very, very small object, which is called a black hole. Why do we call it a black hole? Well, you all have tried to pick up a rock or something and toss it up in the air. So you know that the faster you toss it up and the farther up it will go. So you can imagine that if you throw this stone fast enough away, then as the rock will get far from Earth, the pull of gravity from Earth will get um, weaker and weaker. So you can find a velocity, which is called the escape velocity, that if you throw this rock far faster than that, it will never fall back because it will escape faster than gravity can pull it back. And you can also imagine that the more mass you have, so if Earth was bigger, more mass, more stuff, then gravity pull would be stronger, and so the escape velocity will be larger because you need a higher speed to get the stone to escape. Also, if you were to take the mass of Earth and collapse it down to a smaller object, you get the same amount of mass, but you know that the closer you get to the mass and the stronger gravity pull is. So even in that case, you take the same mass of Earth and you collapse it down to a smaller object, then you get a higher escape velocity. Well, so let's imagine that we take Earth of the Sun and we make it smaller and smaller and smaller and smaller. The escape velocity will become larger, 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 meaning that anything that wants to get away needs to go faster and faster and faster. But the bad here is that there is a limit. Nothing can travel faster than the speed of light. So at some point you will compress Earth down to a smaller, 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 get so small that anything to escape from the surface of Earth would need to go faster than the speed of light. That's not possible. So nothing can escape, not even light. That's why this will look like literally a black hole. Nothing, not even light, can escape. So how small do you need to do to make Earth? Well, if you were really to squeeze down Earth, you would need to have it 9 millimeters, something like this, less than half an inch. So that's not possible, of course. But the sun, you would have to compact it down to about less than 2 miles. So that's not going to happen because the sun doesn't have enough gravity to collapse that much. But bigger stars, gravity is the force that will push everything together and create a black hole. So the thing is that then everything will keep collapsing until you get just a point, but we will never know what happens inside because no light can escape from this event horizon around the black hole. And you might remember that back in 2018, I think, astronomers took the very first image of a black hole. What you see here is gas that is very hot, so it's red and yellow, and is falling inside a black hole, a big black hole that is in the center of a galaxy called M87. And then you see that round dark patch in the center. That's the event horizon. That's where anything inside that sphere cannot escape anymore. So this is what's a black hole. And so now let's go back to our gravitational waves. Again, we have those two black holes that are orbiting around each other. And as they orbit around each other, they create gravitational waves, those shades of green, those ripples in space and time, right? The more and more gravitational waves they emit, and the more energy they lose. And so they're falling one into each other. As they fall one into each other, they go faster, faster, and faster, and they deform space and time more and more and more. And so you get more intense gravitational waves until they collapse together as a final burst of gravitational waves, and then they're just creating one single black hole. How does that look when it gets here on Earth? Well, this is a representation, a graph of the actual data that we detected, the distortion of space and time that we measure with our instrument. So as time passes, you move around the horizontal axis on this graph. And then we have two observatories. One is in Hanford, Washington State, and the other is in Livingston, Louisiana. And you can see that as time passes, there's an oscillation stepping in, and that's the formation of space and time created by the two black holes. And you notice that it gets bigger and bigger, higher and higher amplitude, and also the maximum, the peaks get closer and closer in times, meaning that the frequency of the pitch of the signals get higher and higher. And this is exactly what happens because the two black holes are moving closer to each other, and they get closer and closer and closer and creating gravitational waves that are higher and higher in both amplitude and pitch frequency. So we can detect this using hundreds of computers that look at the output of our detector in real time and look for signals that look like this. Every time we have one of these signals, we send out an alert to all the other astronomers in the world within few minutes so that they can try to point their telescope to the position in the sky we are pointing them to and try to see if there's something new after the collision of those two black holes. So you don't expect much to be visible in any other way but gravitational waves when two black holes collide, just because they're black. But if you were to have two neutron stars colliding, then something interesting might happen. And indeed, a few years after the first discovery, so about 7 years ago, there was something very interesting that happened like that. So here we had two neutron stars. So remember, when a star dies, it can create a neutron star or black holes. The two neutron stars were moving around each other and started spinning around each other. They were creating gravitational waves. But now we're not talking about black holes. We're talking about two gigantic balls of neutrons. So when they collided, they generated an enormous nuclear explosion. And so after that, you actually expect to see something in the sky, to see a ball of gas, superheated, super hot, generating a lot of light and gravity and electromagnetic waves and all of that. Just to give you an idea, what we're talking about is take the entire mass of the sun or more than that and squeeze it down to a ball which is about 10 miles in radius. So it will look something like that over a big city. Of course, that would be not possible because the city will be destroyed by this. But this is a super heavy and small object. Every cubic inch would weigh more than 7 billion tons. So basically, it's a mass of Mount Everest on a teaspoon or something like that. So it's incredible to think about it. Nevertheless, when some stars dies, they create neutron stars. And we were able, here on Earth, to detect the ripples in space and time, the gravitational wave generated by the collision of those two neutron stars. So mind me, gravitational waves are not sound waves. They are vibration in space and time itself. But it so happens that the gravitational waves generated by two neutron stars, we can detect them with our instruments and convert them into sounds. So that's the sound that you can hear with your ears. So what I'm going to play now is the actual signals we got out of our detector while the two neutron stars were colliding. I should say not while the neutron stars were colliding, because the collision happened millions and billions of years ago, because those neutron stars were very far. But as the gravitational waves swept through Earth, we were able to detect them. So what you hear here is the rumble, it's a background noise of a detector. So this line shows you time passing. So horizontal is time and vertical is frequency. As time passes, you see this brighter line showing up there. That's where there is a little bit of signal, a little bit of a gravitational wave signal at that particular frequency. You see that it's getting more intense and higher in frequency. Near the very end, you will hear it if you listen very carefully. So did you hear that whoop at the end? So that's the sound converted from the gravitational waves of two neutron stars that collided hundreds of millions of years ago in a galaxy far away, hundreds of million light years away. I think it's amazing that we were able to detect the ripples of space and time generated by those two gravitational waves, and we can actually listen to them. But that was only the beginning of the excitement, because as I told you earlier, the collision of the two neutron stars actually created a gigantic nuclear explosion. A nuclear explosion generates gamma rays. So now this is what you're listening is a simulation of how the gravitational wave signal would sound like without noise. And about 2 seconds after the gravitational wave signal was detected from us, the Fermi satellite, which is a telescope in orbit around Earth that is able to detect gamma rays, detected what is called a short gamma ray burst. And this was the first time we proved that, yes, those gamma ray bursts are coming from the collision of two neutron stars. That was even more exciting because now not only we detect the gravitational waves, but we were able to see gamma rays, electromagnetic radiation, very high energy light coming from it. But more than that, our gravitational wave detection was able to pinpoint the location in the sky where the signal was coming from. So at that point, almost all astronomers in the world ran to their telescopes and tried looking into that area to find the aftermath, the new star that is grown after the collision. That was not really a star, it was just this cloud of gas that was very hot. 10 hours after the gravitational wave signal was detected, astronomers discovered a new object emitting light. So you see this big round thing in the center here is a galaxy far away. And this dot indicated by the two arrows is the new object. This is the aftermath of our collision. And you can see that in a previous image taken 20 days before, it wasn't there. Then this is an even better image taken by the Hubble Space Telescope. And you see this galaxy far away, and this dot here is the new cloud of gas that was generated after the collision. This inbox here, this box shows this, zoom in there, but shows you how this new object was fading slowly over time. It was fading because after the collision, we created this big, hot cloud of gas that then by emitting radiation was cooling down over time. So this was a remarkable result because we were able to see gravitational waves, to find them in the sky, to see a gamma ray coming from that, and then to observe the aftermath in all kinds of optical and radio telescopes. And astronomers did that for days after the collision. And they did something which is called spectrography, which basically means they're looking at the different components in the color of the light coming. And this graph here shows you that as time passes, the main color shifted from being in the green and blue to being red and then the infrared. And this is what we expect when the cloud of gas is cooling down. But even more than that, an astronomer can, an astronomer can look at the peaks and the little dips in these spectra and understand what chemical elements are present down there. And so we proved for the very first time that most of the heavy elements that you and I are made of, everything heavier than iron, most of them are really generated in the collision of neutron stars. So we can quite literally say that you and I and almost all we know here on Earth is made by the dust or the element, the aftermath of the collision of neutron stars. So that was not the only event that we detect, even the 2-1, black holes colliding and these neutron stars. So what we do here is from time to time, we turn on our detectors and we just see what happens in the sky, what's coming through, what gravitational wave signals are arriving. And we do that for months and years at a time. This representation here shows you in the vertical scale how big the objects are measured in terms of solar masses. And so you see down here the first 2 neutron stars that we detected. So every one is about 1.5 times the mass of the sun, colliding, merging, and creating a bigger object, probably a black hole. But we detected a lot of other much bigger black holes, up to 200 times the size of our sun. So there's really a lot of collision from black holes out there happening all the time. So by now, maybe you have a big question, which is, all right, great, you detected all those gravitational wave signals. How do you actually do that? Well, first of all, let me explain what it means that the gravitational waves deform space and time. So imagine that you have a ring of objects out in space without anything perturbing them. They're just sitting there, nice and quiet. So if a gravitational wave is coming through perpendicular to the screen, what it does is to literally change the distance between objects in an oscillating way, because gravitational waves are waves after all. Remember what we said at the beginning, gravitational waves are periodic oscillations. But they do this characteristic thing that if they squeeze one direction, at the same time, the other direction gets longer, gets pulled. And then being an oscillation, it goes back and forth, right? So this is an exaggeration, of course. No gravitational wave would create such a big effect, otherwise we would be feeling them the whole time. Our detectors are very long. They are 2.5 miles long, 4 kilometers, and we monitor the change in that distance to see the event, the passage gravitational waves changing that distance. Even over 4 kilometers, 2.5 miles, the change in distance is so small that if this is a hydrogen atom, to see that change in distance, we would have to zoom in and go in, pass even smaller than the proton in the center of the atom, and we would see a change in the distance, and we did see a change in that distance, which is about 1,000th the size of a proton. So it's a very, very small change. Nevertheless, we managed to build detectors that are sensitive enough to do that. How? Well, we use an instrument called a microscope interferometer. All right, it's a laser. A laser, we send this laser to a mirror that transmits half of it and reflects half of it. So a laser is just a light wave. So half of this wave travels 4 kilometers one direction, is reflected back by a mirror and comes back, and the other half travels in the perpendicular direction. So if the two distances are tuned properly, the two waves coming back, one will go up, the other will go down, as we said at the beginning, and they will cancel out. You have destructive interference. But now, if a gravitational wave is coming by, what happens is that one arm is going to be a little bit longer and the other a little bit shorter. The laser going in the longer arm will have to travel more and will come back later. And the laser going to the shorter arm will come back sooner. So they will not cancel, the two waves will not cancel out each other. And you still have some light there. So this is how we can convert a change in distance due to gravitational waves into a change of light, and then our detector can see, and we can convert gravitational waves into a signal that then can be recorded. The real thing looks a little bit more complicated. So we are flying now over our detector in Hanford. So you can see the desert of Eastern Washington out there. And now we are soon going to be switching to the detector in Louisiana. You see the swamp and the woods out there. So the laser and the beam splitter is in this building in the center. And then you see the tunnel with the 4 kilometers long where the laser goes. Now we are flying inside our tunnel. This is an animation. Soon we're going to go into the actual steel pipe that contains the laser. That is what the laser would see or what you would see if you were in there. Of course, everything we have is in vacuum, meaning that we have to pump the air out of our instruments. The big tanks you see here are actually vacuum enclosures, vacuum tanks. And we do that to avoid contaminations. I mentioned briefly at the beginning that we have two detectors. One is in Washington State, you're seeing it now, and the other one's in Louisiana. So the two corners of the United States. You might wonder why. Well, the reason is that each one of these detectors is pretty much omnidirectional, meaning that it can detect signals from any direction in the sky, which is great because it would be hard to point a telescope which is 4 by 4 kilometers. But then it means that with only one detector, we would not be able to decide where the signal is coming in the sky. So what we do is exactly the same thing that your brain is doing right now with your ears. If you think your ears, they cannot tell the direction the sound is coming from, but the brain can measure the very small difference in the time when my voice arrives to your right ear or to your left ear, and from that decide from which direction the sound is coming. We do exactly the same with our detector. We measure the different times of arrival of gravitational waves of the two detectors, the two observatories. And from that, we can pinpoint in the sky where the signals are coming from. I mentioned briefly that all our instrument, optics, and the laser and everything are kept into vacuum. That's for two reasons: to avoid contamination, dust and stuff to fall in the laser, but also because otherwise vibration in the air, sound, will give us a signal, a disturbance, which is way bigger than anything we're trying to measure. And so you can see here how all our optical benches are in vacuum. This is a view of the corner station with a lot of different vacuum tubes and vacuum tanks. Our mirrors at the end and the splitter are actually very big. Those are 40 kilograms, like 90 pounds, pieces of glass, super pure, super advanced glass. And of course, we cannot just have them sitting on the ground because the ground is continually shaking because of a lot of small earthquake happening all the time. And so we have to suspend them to complicated system to isolate the motion of the mirror from the vibration of ground. So this is all the kind of technology that goes into detecting gravitational waves. So I hope I convinced you that we started this new era of gravitational wave astronomy. And so for many, many decades, we were looking at the universe with different kind of colors of light, different parts of the electromagnetic spectrum. Now, finally, we open a new window in the universe using gravitational waves. And the future gravitational wave is a bright future because we have spent already 3 periods of time calling observing runs to detect gravitational wave signals. And since May 24th of last year, the LIGO detectors have been back in operation with some brief interactions here and there, but still back in operation, detecting more and more gravitational waves. So up until the very first 3 observing runs, we detected 90 total signals from the collision of neutron stars or black holes. And now in the new 4th observing run that started about more than a year ago, we already have a lot more than that. We brought the total of signals that we saw up to more than 200. We are now able to see a detection every 3 days or so. So this observing run will continue all the way until the middle of next year, and then we will stop again to improve our detectors even further, and so make them even more sensitive. That's all I wanted to tell you today. I want to leave you with this last slide that gives you some other pointers. If you want to know more, you can contact me, or you can go to LIGO.org or follow the LIGO Laser Interferometric Gravitational Wave Observatory on Facebook, X, all of that. Thank you so much for your attention, and then I'll give it back to Adrienne, and we'll see if any of you has any questions.
Yep, I'm going to open the chat, guys. Thank you, Gabriele. I never get tired of listening at that presentation.
Thank you.
I never do. And you always come up with something new that I didn't hear before. So I'm like, hey, I didn't hear that one before. So guys, let me find, if you want to talk, you can come off mute. Otherwise, the chat is open. So somebody can, I think it is. Yeah. Yep, it is. Any questions? I know you guys have questions. You're science guys. Okay. Here we go. Yes. Yes, you do. You weren't that late. Here. All right. Anybody want to know about studies? Talk about studies. What do they need to know to get into gravitational wave astronomy?
That's a great question. So, building and operating and making an instrument like that work means that we need really a lot of different skills. So we are not all astronomers or all physicists doing this. We are, no, our group has a lot of engineers because you have to build the actual instrument. So we have electronics engineers, we have optical engineer, mechanical engineer, civil engineers, because we have to build even the buildings and the pipes and all of that. And then we have people that operate interferometers that have master degrees or bachelor degrees in technical sciences or topics. So if you want to become an astronomer, then you have to learn physics, you have to learn mathematics and all kind of science. Similar if you want to become an engineer. And every big experiment, every big observatory in science needs a lot of different expertise. Technicians, engineers, but even people that can do the administration, that can help us, manage the people, manage the funds we get, all of that. So there is a lot of different skills that are needed in this.
Good, thank you. Anybody interested in doing gravitational wave science? Some of them was probably the first they've ever heard of it. So anything else? What new technology out there for detections? Are you guys coming up with new ways maybe to get further into space or anything like that?
Yeah, so we are always working to understand what limits how sensitive our instruments are, so how far in the universe we can get, right? And so that's the reason why we observe gravitational, the universe in gravitational waves for a year or a year and a half, and then we stop and we install new components, update of components, higher power lasers, more stable lasers, better mirrors that have better optical properties, or we improve the way we isolate the mirrors from the motion of the ground and all of that, right? So that's something that we always do. So that's why in the middle of next year, we will stop observing the universe and we will start doing work to install new components and improve our detector for probably a couple of years with the goal of going back and being even more sensitive. So being able to reach even farther in the universe and see more stuff out there.
Wow. Did you notice the more that you move out, is it more activity or being that I would imagine that the further out you go, um, all of that took place so long ago that maybe it's more busy. And
Yeah, so right now we are still reaching out to a relatively small fraction of the universe. So we are able to reach out maybe to 2, 3 billion light years away. So looking back at what happened 2, 3, maybe 4 billion years ago. So that's still considered kind of the local universe. So there were a lot of stars, there's a lot of black holes. So we don't see the universe getting more or less busy. Of course, the farther away we get, and the more stars and black holes are in that volume, right? Because if we double the distance we can reach, it means that the volume of universe we are observing goes with the third power, the cube of the distance. So doubling the distance means that we can have 8 times more black holes colliding, right? So far,
right,
the farther away we go and the more stuff we see. We have already an idea of a future detector that we will build maybe in the next 10 to 20 years. It's called Cosmic Explorer, and it will be much bigger, 40 kilometers long, so 25 miles long. And we call it Cosmic Explorer because it will be so sensitive that it will be able to reach so far in the universe to the point that there aren't black holes anymore because you're going so far in the past that the stars weren't born yet. So there were no stars.
wow,
So we will be able
wow.
to see all the black holes colliding in the entire universe. But maybe I will retire before that. Who knows?
Yes. Wow, this is neat. Okay, someone asked what kind of damage can gravitational waves do?
That's a great question. So the gravitational waves that arrive here on Earth, they don't cause any damage because they're very, very, very weak. But if you were to be very close to those two black holes colliding, the gravitational waves will take you and squeeze you and then, make you imagine you get very thin and very long and then very short and very large. And so they will tear you apart. So they will destroy everything, tearing everything apart. I see another
Is there,
question in the
yeah,
chat
yeah,
there.
yeah.
Is there
Can you
only
see?
one black hole or there's more? No, there's a lot of black holes there. Every time two black holes collide, they create a new one. So all the signals that we saw were hundreds and hundreds of different black holes. So there's actually a lot of black holes out there, but they're all far, very far from Earth. So we're in no danger anytime soon.
Somebody, let's see. Isn't there supposed to be more because they're merging?
Yeah, exactly. The more, you know, You have two black holes and they merge, they create another bigger one. Then there are other black holes that will merge together. So it's continuous merging of black holes. It was actually a surprise after when we started the very first time we started turning on our detector to see how many black holes are there out there. You're very welcome.
Yeah,
Soccer
thank
game.
you. Yeah, can't miss soccer. We're
And
almost
your
done anyway.
priorities.
Thank you for coming. Okay. Any more questions for Gabriele? We had a tour, what, a couple of years ago, about a year or so ago,
Maybe a
of
year or two ago, yeah.
yeah, the facility where Gabriele worked. So maybe we're going to do that again, and if he allow us.
Of
And
course, you're welcome anytime.
yeah, and I asked Mr. T if you guys want to join us. You can see that facility up close and personal, give you a better idea how everything works. And it says, let's see, Sophia asks, oh, I'm sorry, Gregory. Let me get to Gregory first, Sophia. Then I'll get your question. Are the ways between pulsars and black holes different?
Yes, they are. So when two pulsars that are neutron stars, when they collide, since they're smaller, they move faster. So the bigger the object is, the bigger the mass, and the slower they move. So actually looking at how fast the signal evolved over time, the waveform, we can tell how big the objects were. The slower they move, and the bigger the objects are. So they are different, and that difference is really what we use to understand what we're looking at. So what's the largest recorded black hole? So the largest black holes that we recorded making gravitational waves was about 200 times the mass of our sun. But we know that with other waves, we have a very solid evidence that at the center of every galaxy, there is what is called a supermassive black hole, which is 1,000,000 times the size of our sun. So those are much bigger black holes.
Good question. That was a good question.
Yeah,
Both
great
of them.
questions.
Yeah,
Yes.
all of these are good questions. I think I see one more.
Yeah. So if two galaxies collide, what would happen? Well, surprisingly not much, because there's a lot of empty space between stars, right? So the two galaxies will just pass through each other, and there will not be any big explosion or any collision of stars. Of course, the shape of the galaxy will be completely disrupted, but not much will probably happen to the stars.
Right, because we're actually colliding with the Andromeda galaxy, right?
That's true. And
So
if we wait a few billion years, we'll see the collision. So maybe we can
right.
stick around.
Our galaxy just gets bigger. That's
Yeah,
not that there's it's so vast that everything will just
there's a
form
lot of
another
space between
galaxy.
stars. Yeah.
Yep.
So another good question there. Are galaxies formed from black holes? Well, no, it's the other way around, right? So black holes are formed from stars that die. So galaxies are made of stars. So that's why in the galaxies there are a lot of black holes, because galaxy form, stars are born, and then they die, they create black holes, and then the galaxy get filled with more and more black holes as time goes on. Are there any other beings in space other than what was mentioned that combine are affected by gravitational waves? So everything is affected by gravitational waves. You, me, planets, everything. And also everything that moves generates gravitational waves. So if you are jumping up and down, you are also generating gravitational waves. The thing is that you are much lighter than a star. And so the amount of gravitational waves you create, the amplitude, the intensity, it's very, very small. So it's basically impossible to see it. But anything that is big enough will create gravitational waves. So the biggest things we know out there are stars, and especially when they get very compact, like neutron stars or black holes. So those are the main things out there that create gravitational waves. You're welcome. Can we make gravitational waves to communicate with other beings in space if there are there? Well, so to generate the gravitational waves, as I said, you would need big things like black holes. So in theory, if we were able to create black holes and have them collide, we would be able to create gravitational waves. Right now, we are not able to do that. So it seems unlikely that that would be a reasonable way to communicate with people out there. But if they were able to create a gravitational wave detector like the one we built, they would be able to um, detect our signals. But today we're not able to do anything close to that.
Here's one more.
Yeah. Do you expect the LISA mission to provide any new discoveries or evidence to support our understanding? So the LISA mission, for those of you who don't know, it's a laser interferometer space antenna. So the same idea of using an interferometer to detect the gravitational waves, but it will be in space, in orbit around the sun. And it will be very big. So we're talking about 1,000,000 kilometers. So really huge. The fact that it's so big, it means that it will be able to detect the gravitational waves at a much lower frequency, which means we'll be able to observe much bigger objects. So they will provide new discoveries and new information on gravitational waves because they will observe a different kind of black holes, much bigger, objects that are much bigger than the one that we on Earth can detect.
That's the first I never heard of that one. So, can you create or can something be created to ride a gravitational wave?
Well, there are actually very, very weak, so you can't really do much with them, and they interact very weakly with matter, with stuff. That's why it's so hard to detect them. So a lot of gravitational waves are passing through us, and we don't even feel them. So it's hard to imagine that we will be able to surf a gravitational wave, right?
Right.
So how many black holes that we know of exist? I cannot tell you the exact number. I can tell you that we at LIGO detected more than 200 collision of black holes. So we can, from that, predict how many black holes there are in a typical galaxy, how many there are out there. And there are a lot. I don't have a precise number, but there are a lot more than we expected at the beginning. And a lot of them are colliding.
Any more? Okay, that looks like that's it. We had 2 minutes to spare. That was a great presentation as usual, Gabriele. I just love listening to this topic. I'm a space person, as you know. But I think he's coming back. Aren't you coming back later on? Um Next
Whenever
year.
you need me, just
Yeah, I
call.
think we have him down next year. Like January, February sometime, guys. So tell your friends and invite them because this was a very good presentation. And you could always use this information going forward. So I have all of the guys from Mr. T's class. I already took roll and I will give it to him when he comes back on Monday, I suppose. But thank you again, Gabriele. Thank you guys for taking an hour out of your Friday. I know the Dodger game is on and all that. And we appreciate you. Okay. Thanks a lot.
Thank you very much.
All
It's
right.
always a
Thanks again,
pleasure.
Gabriele. I'll talk to you soon.
Talk to you soon. Bye
All right.
bye.
Bye bye.